You run some registry diff tools, some other types of maybe live process tracing, whatever tools you like to use, you throw it in there, and then when it's done, you have a report, and then in VMware, you just hit the restore snapshot, and you're done. Problem with that is becoming that increasingly the malware authors are wise to what people are doing with VMware, and so they're putting in detection for VMware, and it's really, really easy. There's multiple ways you can do it, and this isn't just VMware specific, but there's some of that in here. The easy way, just off the top of your head, that you can think of, most of the VM machines are going to have some virtual NIC, whether it's QEMU or VMware or Box or whatever have you. They're going to have some virtualized NIC driver, and a lot of times they'll put a special MAC address prefix on that. VMware does it. Not sure if QEMU does it, but I think it does. So real easy way to detect. What's my MAC address? Does it start with this prefix? I'm running in a VM. So there you go. VMware has a notorious I/O backdoor, 5 lines of assembly, and you can find out just by doing an I/O call, I'm running in VMware, I'm not running in VMware. There's other things. There's CPU descriptor tables that have to be relocated sometimes, and this is another way that can clue you off. If these descriptor tables show up at the wrong place in memory, then you say, I'm being virtualized. There's other more vague things that people can look at. They can run, say, an exception, and using the structured exception handler, on a stock system, on real hardware, under Windows, takes a certain number of cycles. And if it ends up taking longer than that because the VM is doing some extra work on the back end, there I'm running in a SANnet, or I'm running in a VMware, in a virtual machine. So bottom line, these don't always behave like a real system. It's real hard to make them do that, especially with the closed source type stuff. I mean, there's a patch for one particular version of VMware out there that you can fix some of these problems with, but there's other problems that just can't be fixed. And like we said, there's already malware out there actively using these checks and refuse to run under a virtual machine. So if we want to do away with the whole virtual machine concept, what is our basic stumbling block? It's the fact that it takes us a long time to sit there and re-image a Windows machine. We might have a DD image somewhere, but this is a lot of manual labor. So I was thinking, let's automate this as much as we can and make this useful. And this kind of turned into the whole SANnet for me. And as an added benefit to what we're doing here in terms of setting this up on native hardware and maybe even some open source back-end stuff, is that we can control what the environment looks like. We're not limited by whatever the VMware people tell us we can change. We have full control over however we set it up. And because of that, and because each person that takes the information from my talk today and goes and sets up their own system is going to do it slightly different, this makes this a real heterogeneous environment. So we're not going to give the bad guys one simple way to detect that they're running inside of this environment. So the software that I've kind of compiled, cobbled together, Linux image and some scripts, is basically, I'm calling it Truman, stands for the Reusable Unknown Malware Analysis Net. So basically, I developed the software in-house because I needed to solve these two problems, which was the virtual machine detection, the VMware, being easily detectable, and plus, I wanted to be able to isolate the malware I'm looking at from the network, because I don't want it to spread. It'd be terrible if it got out, on our internal network and spread. So it needs to be isolated, but at the same time, most of the malware you're analyzing nowadays has to interact some way with the web. Maybe it's a downloader and it's just going to go out there and get a web. Maybe it needs a DNS lookups. It needs some sort of interaction. But I don't want to give it that interaction. I don't want it to have that ability. So basically came up with this concept, called it a SANnet, and there you go. So what I'm saying a SANnet is, and you can call it whatever you want, but basically you could compare it to a sandbox, but you've got more room to play in. You've got a simulated internet. On the other side, you can look at it from, how is this different from a honeynet? It's basically because a honeynet has to have some interaction with the real world. You're looking at real-time attacks coming from either actual attackers or infected machines that are actively trying to interact with your honeynet. So I don't want to have this interaction, so I have completely isolated it, and we're just going to simulate everything that it needs. So the key concepts we come away with that make this a SAN net to me is the automation of the re-imaging, the network simulation, and then on the back end, finally, the change analysis, so that we can tell exactly what did happen when the code ran, and as much as we can tell about the behavior. I'm going to stop and get a drink of water. I'm really thirsty. So the process is pretty simple. I mean, it's pretty obvious. You boot first up the pristine, what I call the pristine target OS. Whatever OS your malware runs on, most of the time when I'm analyzing, it's Windows. After we run this malware for a set amount of time, we boot into a second image. Now this time, I'm booting a Linux image, and we use this just as a platform to copy and restore this image. We don't actually do the forensics at this point. All we're doing is we're copying everything we can get off this system off to another system where we do the analysis. And after that, we just restore the original image back over to the pristine OS, and then the next time it boots back up into pristine OS or Windows or whatever you have, and you can just keep repeating this process and analyze malware all day long. So in terms of how to make this happen automatically, you looked at, how can we do this in a way I don't have to step in and interact with the machines. I don't want to have to be there. I want to be able to be in a remote location and do this and just have it kick out. So Pixie Boot actually comes in really handy here, because we could use a Pixie Boot server to basically tell the machine every time it boots, this is what you're going to boot today. And Pixie can also be told to override, don't load a image from the TFTP server, but actually load the local OS. So that's exactly what we do with it. So this is actually the TFTP boot directory on the SANnet server. Basically just has the image, and that maintenance image doesn't actually go in there anymore. That's been removed. But everything basically happens in this Truman image.gz. That's just a a little minimal 16 megabyte Linux distribution. And there's a Linux kernel to go with it, and a splash screen, and then the regular Pixie configuration. And what we do, in order to rotate what it's going to boot, there's a pixielinux.config directory that we have our information about what would usually go in your Lilo or Grub bootloader, basically the same information. So we're just going to swap between the Truman version and the normal boot version as we boot, and the system's going to tell us what it's booted into now, and then we'll say, aha, we're going to switch it. Next time you boot, you're going to do the other one. So basically, in a cycle, that's basically everything I've just said, what a redundant slide. Okay, so that's what the splash screen looks like. But one important thing, I guess, to notice here, I don't really mention it anywhere else, is that there's multiple boot options besides just the two that I mentioned. There's the save and restore boot and the normal boot, but you also want to be able to independently, maybe you only want to save off an image and you don't want to restore it yet, you want to keep working on it. Or maybe you just want to restore, you don't care about analyzing whatever it was, you just wanted to grab some dropped files and you just want to go, so you might run restore only. And then a maintenance mode, which basically just boots up into a shell. So that's pretty much it for the boot setup. Now what we're going to do, since we've got this server out here and it's already acting as a Pixie Boot server for us, it's connected over a crossover cable and makes a nice little network together with the client. We're going to use that as our default gateway for the client. But instead of routing traffic like a default gateway would, we're just going to absorb everything to the local machine using IP tables in this case, or you can use the packet filtering on OpenBSD if you want to adapt your system that way. But basically, anything that can absorb all the traffic and then feed it to local servers can make it work with us. And then what we do with those is we make it appear as if it's listening on every port or whatever ports we want to serve up. And we also feed it fake DNS addresses so that it also, anytime it tries to look up an address, it doesn't just get the same IP address, it gets different random IP addresses, but they all go here. So in effect, this machine becomes the internet for that client. And here's just a very simple diagram. This is exactly how I have it set up. I mean, crossover cable couldn't be simpler. Your default route to the server. We use the non-RFC 1918 addresses because we want any malware that's going to be adverse to running on a local network, that's going to try to tell if it's on the internet at large, we want it to think it's on the internet at large. So I just picked out some IP addresses at random. I suggest you change these if you do this, just so that would be an easy way that the bad guys could say, aha, I'm on this IP address, aha, I know where I'm at. All right, here's a little bit about the rules and how they work. Basic IP table stuff, but you could also do it with the BSD stuff. So a little more about how we address each one of the services. So what we do is we provide basically for the services that we care most about, like HTTP, SMTP, IRC, FTP, the kind of things that most malware is going to be talking on. We provide our own listener. And what I've done is I've just written some simulated servers in Perl, just real quick, implement as little of the protocol as I can get away with type stuff. You don't have to use my scripts. There's stuff from the HoneyD project work just as well. You have your own, or you can use the real servers. Now, if you use the real servers, you've obviously got to be careful that you're not also introducing maybe a vulnerable version of Apache to a piece of malware that exploits Apache. So you want to be careful in that regard. But for the most part here, you can throw anything out there, and if you just redirect your IP tables to the service, then it thinks that it's talking to whatever server it wanted to talk to. Now, for everything that we don't know, it's going to try to go out on weird ports. We're never going to be able to guarantee what it's trying to talk to ahead of time. So what we do is we provide a default listener, and all this default listener does is receives packets and records, and if it gets a packet, it'll send back a couple of new lines. And in this way, it hopes to keep that communication open as long enough. If this server, maybe it's trying to send an exploit, and this exploit doesn't really care about the responses it's getting back, maybe it's just looking for a response, any response. So it'll get that response, and it'll keep sending the rest of the exploit. So these are some of the scripts that I've included here. I call everything my faux scripts, and everything starts with faux DNS, faux SMTP, faux IRC, whatever. And like I said, your own scripts, whatever you want to do. Another key aspect we want to do here, we don't just want to emulate whatever services, but we also want to see what's going on. So we capture everything, every packet that's sent, we capture that and log it for our later analysis. And also look at it, as it's going on, so we can kind of tell. Because a lot of times you may not have a service listening on a port, it's trying to send SYN packets, and you don't see any content flowing across because you don't have anything listening. So you might have to go back and tweak it. And it is a lot of tweaking. This is not a fully automated system. I mean, you're going to run into malware that doesn't do what your SANnet expected. So you're going to have to go in and you're going to have to adjust the IP tables rules, set up another server, that's going to be whatever. I mean, that's just the way it is. What we want to do, though, is we want to look, even when it's trying to send out stuff via HTTP, for example, it wants to go get a second stage download. What we're going to do is we're going to capture that request, we're going to go to that website, we're going to pull down that executable, and we're going to put it, say if we're running Apache as the HTTP server, we're going to put in Apache exactly where it expects to pick it up, and we're going to let it run a second time, pick up that malware, and see what it does from there. I mean, it is kind of a manual process, but this is the price you pay if you want it completely isolated from the internet. Talking a little bit about the IRC, botnet type stuff, this is one of the biggest things that we're fighting and a lot of people are fighting right now, so I thought this might be of some interest to let you know how the SANnet works in that respect. It makes it really, really fast to basically find out who, what, where, and when of an IRC botnet. So what do you want to know? You want to know, say you want to log into this botnet, you want to spy on them, see what's going on. You want to know, first of all, where the command and control server is, what port it's on, what protocol. Hopefully it's IRC, because that's very easy for us to get right on there and emulate. The nickname is going to be very important, because if you go in there with whatever nickname and it doesn't match the rest of the botnet, you're going to stick out like a sore thumb. The guy's probably going to DOS you to death, and it's going to be the end of the game. So we want to know exactly what the bot sends in order to log in, so we can pretend to be one of these bots. We want to know what channels they're joining and channel key they may be using to join the channel. And I have a script that I provided in here that basically not only simulates the IRC server, but it also dumps this stuff into a nice little text file for you later, so you can replay this back. I've got another script that you can use, or you can use Telnet, and you can basically just paste this output right back into it. You just connect to the command and control server, you paste out whatever the SANnet told you was happening, and it sits there and it just basically stays logged in, just stays logging as much as it can for as long as it can. And the only difference between it really and Telnet or NatCat is that it sends pongs for you. If the IRC servers are going to keep trying to ping you to see if you're alive, it'll send an automatic pong, so you don't have to stay there and watch it. You can let it run in the background. Okay, so here's like a sample of an actual capture that I did a while back. This is the SANnet IRC log. Basically tells you, this is actual just a TCP dump capture, but it says, it looked up this command and control server, bled.darkassetonline.us, and then tried to connect to it on port 8080. And then we saw in the capture, these are the user details, and this is what it was joining. I love Diablo, and channel key Diablo, and we all know who Diablo is now because he's sitting in jail. But this is basically us spying on his session here. We start up the IRC raw.pl, connected to it, and here's his little IRC session. And all the blue stuff here on the screen is what we are sending, basically, that we just pasted in. And all the black stuff is the rest of the stuff from his network. And so you can see, if you look, as soon as the bot logs in, it's going to do this .dl command. It's going to download this socks.exe executable from another server. So that's something that was important to us, because now we have that piece of malware where we can follow that trail and see where that leads. And probably to spam, but okay. And we also see that Diablo has a few other friends that didn't seem to get arrested there, Binge and Legion. I wonder where they're at. All right, so that's basically how the network capture works. Now going on to post-mortem. And I don't go into a whole lot of detail here, and I don't have actually that many tools on the system. I basically just set up a framework, and you can use it, whatever forensic tools you like using. If you like using, just diff, then that's great. I like it. If you want to use MD5 deep plus SHA-1 deep, because you don't want to just use MD5 deep by itself, obviously. Is Dan in the room? Then you can do that too. But basically, you can mount this image after you have it, back safely on your SANnet server. You can mount that NTFS file system, for example, on Linux, and then you can just do a recursive LS, and then diff against the original recursive LS, and that'll tell you what files have changed potentially, as long as they obviously don't have the same timestamp and size. You can do the same thing. There's a tool called DumpHive that's also on here that you can use to dump in plain text all the Windows registry hives, and then you can diff that against the old, and you can find out what registry keys have been added and changed. And we also do a memory dump. We take the forensic acquisition toolkit's DD, and we just DD physical memory straight to the disk right before we reboot. All right, so I've got a little demo here for you. And I couldn't drag the whole SANnet over here, so I actually set this up as a I have 2 copies of this running. Isn't that great? All right, I actually have it set up as a video so you can actually see everything kind of working in sequence and in order. All right. All right, so this is basically what you might see. If you're monitoring a network and you're looking for attacks, this is the kind of thing you're going to see. You're going to see this botnet tried to send an exploit. This is the LSAS exploit. And then after it does, it sends some commands, and I've got some close-ups. And if you can't read this, there's some close-ups. But basically, this is the standard stuff. It sends some shell commands to Windows to download via FTP this file, bingu.exe. And since he's nicely given us the username and password to that FTP server on the infecting host, we can go grab a copy of that. So now we've got something to look at here. So there's the boot screen again. A couple of machines, crossover cable. No big whoop. All right, so here's the client booting for the first time. We're going to first basically default to the local boot system image, and we're booting up Windows. And this version of Windows here has been vastly sped up, you'll notice, for the boot time. All right, so the first thing it does is it runs a batch script that we've got on the system, and it reports in and says, hey, I've booted. And then it tries to retrieve a file using wget from a queue on the server. And if it can't find that, it'll sleep for 60 seconds. Back on the server, what we do is we copy our executable we want to analyze into this queue, and then the next time this thing wakes up and gets it, it'll execute it, and then it'll sleep for a preset period of time. Here I've got it sleeping for 10 minutes. And at the same time that we copy that file into the queue, we're also going to start some monitoring scripts here. And so what we see here, if we've got our ngrep capture going on of what's actually happening on the network, first it tried to do a lookup for null.routing.vu, and then it tried to do an IRC protocol connection on 6667. So after we let that run for a while, do its thing, we found out the critical information from that. Now we're going to talk about the post-mortem phase. Right now it's dumping physical memory using this memdump DD to a file mem.img. At this point you can run any other forensic tools that you have. I like SecCheck. I don't have it included in the distribution. You can get it from mynetwatchman.com. It's a real good thing. It just tells you everything that's running on the system and where something hides. Real good little tool. It just dumps out a text file and then we read that later. Not real good for doing a diff on, though, because everything, obviously a process list is going to show up in a different order and it gets all messy. But it's a good thing if you just want to parse through it and find out what's there. Another thing, then we just do an automatic shutdown using the PS shutdown utility, and that's another thing that by license I can't include, so you actually have to go download that or some other tool. So everything so far has been automatic. After we copied that file into the queue, everything's just been running along without our interaction. So the second boot, now the Pixie boot server is telling our client, now you're going to boot the Linux image. And it's going to just boot up the save and restore image. And it starts a DD back to our server on a port that just listens for the DD and then just writes that back out to our save file. So at this point, we've got in our forensics directory, under this directory called Bingu exe files, which is automatically created for us, in the back end, after the save is done and it reports in that the save was successful, the server goes to work running all the back end forensic scripts. So it does all the diffs for us, and so basically we got a nice little bit of output here already that we can look at for the what changed on the file system, or what registry entry changed. And we can run any other tools. The one thing that I have in here for you that you might find interesting is something to work with that memory dump that we made. I've included a Perl script, really, that just reads through that physical memory dump, and it just finds the page table directories and just basically walks through and finds every process, and then gives you the option that you can then dump that process out to disk. And so the cool thing about that is that these guys using packers, well, when it's in memory, it's unpacked. And so when we did our dump, it's unpacked. So now we've got it unpacked. And as it's dumped out, and it's not necessarily runnable, but we can certainly do any strings or analysis like that. And you can see the PMO dump program running right now. This is the output of it. If we scroll up, we see that in this dump that we did of the infected bingu.exe, we find that we've got a couple of things in memory here that it looks suspicious. We've got hellmsn.exe packed by FSG, and then we've also got this task gmr32.exe that's packed by upack. So a couple of suspicious things there we probably want to take a look at. So we can call PMO dump again, we give it that name of that executable. It'll run through again, find all those process directory blocks, and basically say, okay, here's that executable's process in memory space. Go find all those physical pages, write it back out into a virtual memory space, and basically back into an exe, only it's not fully runnable. It's have to be a little bit of a PE header magic there to make that work, but it could be done. I haven't done it yet. So here's actually what the output looks like once you've dumped an executable out. This was packed, But now we can see, we can read in this executable here, we can actually read critical strings that they probably didn't want us to see. For instance, Fareed here, we know now Fareed Esabar, another guy in jail. But basically, he compiled this in Visual Studio under Documents and Settings, Fareed. It's right there for us. So in that case, you know, that's very useful information. Also on the other one, it says has the UPAC header still, but we can read through it now and we can see all the strings that might have been important, including the server it's going to connect to. And if it were going to say connect to multiple servers, that we could see all of those servers and not just the one that we saw behaviorally. So that's also a good thing to try to look at. And now we're running again. All right, so basically we're just going to cat out here. We'll see what changes the system. That's what the output of that dump hive tool run through diff looks like. You know, not that pretty output, but we can definitely see right away what we need to zero in on if we go back and look at those full dumps. The same goes for the LS output. Like I said, it's not pretty. This is very basic. I just wanted to give people a framework. So you can see here that you know, some files have been added to the system. Obviously, the mem dump that we made is written out there, so that changed. And the host file was modified. It wasn't added, but you know, he definitely put in some things in there to keep us from going and getting some antivirus updates. Actually, I haven't found one yet that it could hide from it, because we're doing everything here. I'll let you get that URL. We're doing everything here post-mortem. The rootkit doesn't have the ability to hide from the API. It can't hook the APIs and stop us from reading its memory that way. We're not using the kernel's linked lists of processes like you might find the foo rootkit would be able to hide. In that case, we're not using that. We're just looking for blocks in memory that look like a page directory table. And unless they can hide that, and there is a way they can hide that, but I haven't seen one yet that does it.
What if you're comparing, in this model, you're comparing a known pristine good against an unknown after you run the rootkit or Trojan or whatever? Now, what if you have a machine that's been running on the network and you want to find rootkits on it? What do you compare it against? You compare it against a pristine original to see what's added?
If you had that ahead of time, I mean, otherwise you'd have a pretty big challenge for it. Yeah, I mean, you'd have to have that image ahead. His question was, you know, this is assuming that you have a pristine image and you want to find a rootkit. But what if you want to find a rootkit on a system that you know you're taking offline and analyzing? So in that case, your diff tools and stuff like that wouldn't be good for that. But if you want to do that DD and then run PMO dump on that, that would find the rootkit. Because you don't care what the pristine image looked like with PMO dump. All you're doing is reading through memory, looking for page directory blocks. You know, whether, I mean, and sometimes you might even have duplicate page directory blocks in the memory. You know, so you might end up seeing the same process written out twice, but you're still going to see it. Right, but for rootkits, it doesn't really have an effect, because well, I suppose the files, in terms of how the files are listed on the system, you would be able to see that. But I'm talking about dumping it from memory, and that's the real, I think, core of what it does good is it can actually just get in there and see every process. It doesn't depend on anything that the Windows kernel did other than maintain the page directory table. Yeah.
You mentioned the idea of reconstructing an executable PE file, and I've thought about it before and find the idea really interesting when memory dump. One thing that I've always get stuck on is the initial values of the data section. You don't have those, so if the execute, like, it's going to take a different initial code path.
Yep, exactly.
So how would you address that?
Exactly. Okay, his question is, when you're dumping something from memory, you run into a problem, is that thing's already been running and it's already stomped all over the initialized variables, and uninitialized variables are now initialized, and that's not doing you much good in terms of running it from the first entry instruction and seeing what it does. So in that case, it's not going to build you a perfect duplicate of what that executable looked like going in. What it's going to do is it's going to unpack it for you and make it readable. And you're going to be able to see what it was they were trying to hide with the packer for the most part. So it's not as good as manual unpacking. I don't want to suggest that it is, but it can certainly be a good tool for somebody that doesn't have the ability to do manual unpacking or doesn't have an unpacker for a particular type of packer. I'm taking questions at this point, so anybody else?
Have you run any malware that hides itself in your memory dumping tool?
No, I haven't seen anything that did that. I don't want to go too much detail and give it away for the bad guys, but basically, you could hide it from DD. You could tell DD it's not allowed to read that physical memory part or hook the actual physical memory fake device. So that's one way you could do it. But I don't know of anybody that is doing this, because probably they don't know that you can do this, because right now I haven't seen any other tools that let you do an offline memory dump like this. I've seen one mentioned on a Honey Nut challenge that the guy didn't release the code for. I don't know why, but that's the only one I've seen. If anybody knows of any others, I'm not claiming I wrote the first one or anything, but it's just a tool that helped me out, so I thought I'd share it.
Sir,
Yes?
what are the methods that malware uses to detect that it's running virtual machine?
The methods that they're using right now, mostly they're using that backdoor, the VMware backdoor. There are other methods that have actual working example code for different methods to detect. I haven't seen really anything that I can recall offhand using those methods, but that doesn't mean they're not. But the code is out there. They could certainly use it if they wanted. But I mean, right now, why bother? I mean, nobody's changing the VMware backdoor. It's still there. So if 5 lines of assembly, I mean, why not use that instead? So, over there. If it asks for that, what the question is, if the malware asks for a specific IP and not a domain name, it wants that exact IP. It gets absorbed by the IP tables rules and just gets handled by the server. And that server pretends to be that IP address. Over here in front. Okay. I'm trying to look around and see everybody right here.
On the subject of VMware, are you saying that potentially running something on a virtual machine might be safer than running it on a true host if you're running an exposed server? And the second part of the question would be, what really risk would running something on a virtual environment add versus running it on a non-virtual environment?
Right. The risk you're running from VMware or running a virtual machine and running something in a connected host is that malware has some exploit that can break out of that virtual environment, and that's pretty scary to me. I'd rather be able to see what it's doing. Now, there's also the possibility they could do this with a SAN net, but at least I'm going to see it as it's happening, and I'm going to know what's going on. And if I'm really paranoid, I can just pull the other network cable out of that machine and completely have it talking one side to the other side. No way it could get out.
The reason I ask that is Microsoft is touting using the virtual server as a way of migrating from NT4 to 2000, 2003 servers. So, using a virtual environment, what types of risks does that introduce that, say an NT4 system may not have seen before?
I really don't know. I haven't considered running Microsoft's virtual server at all for this environment, simply because I want to be able to do my actual analysis on Linux. And since they don't have a Linux client for their virtual server, it might as well not exist to me. I'd rather, pay for a VMware license or even try to wing it with QEMU than use Microsoft's.
I was just looking at it from the standpoint of, the application, not so much your environment. What risks that would impose?
I don't know. I haven't researched the whole idea of what you're asking, basically. But obviously, if we're back to malware, we're talking risk of getting outside the virtual machine, basically.
The test I'm trying to figure out how to do is to test existing machines for
Okay.
Now, it seems to me that if you go to a 3-machine model, you can, do your testing with one machine as the target host. Run it pristine, install the known Trojan, the known rootkits, and then use your tool to figure out what to look for, right?
Okay.
And then rerun it against the suspect machine. You can see the same patterns.
Right, it worked backwards. I tell you, it seems like a lot of work. I think what I would rather do is just do a memory dump and just see what's in the memory and see how many processes are running and everything. Now, and you're going to have, and you're going to have to go deeper than PMO dump actually does, and it's probably something that I would do if I had a need for it. But because you also want to be able to look and see if there's any kernel modules. We don't look at kernel space here in PMO dump. So we're not looking to see if there's any malicious kernel module loaded there. We'd see that on the disk, but we're not going to see that in the PMO dump output. But usually kernel modules, I haven't seen a kernel module yet that was packed. I'm not saying there aren't any, but I haven't come across that yet, like a rootkit module that was actually packed itself. Don't know if that works or not. I know there's some more hands up.
Is there a way for you to detect in real time in memory buffer? You're doing the DDs to the machine, but by that time it's already occurred. It's possible.
Are you asking could I tell if the SANET client had some exploit on it that would try to overflow my server? Oh, something that ran in memory on the client, and would it be able to detect that after it was all done, if there was nothing changed on the disk? Nothing in the diff tools, the forensic tools that I have here, would do that. The PMO dump, you could certainly manually look through that and try to find something suspicious. But otherwise, you would probably want to introduce some other type of forensic tool into that environment and try to look for those memory changes and more finely analyze the memory dump. But you could do it. I mean, you've got everything that was in memory, allegedly, as long as they haven't tampered with the physical memory device. Lots of questions. Way back there.
Do you find any value in doing a per process memory dump, like a dump or something, or do you find you get everything you need just for physical memory?
Do I want to do a per process memory dump, you asked, instead of like the... I didn't find any value in it personally. There might be. I'm not really sure. I mean, you got the physical memory. You got pretty much everything that's there. It's pretty easy to reconstruct, actually. I'm surprised there are not more tools out there that let you just take the memory dump apart like this and do it. And it's probably because I'm coming from a Linux background and trying to use open source tools, and other people that might be doing forensics on Windows might be coming from the, I'm going to use like a debug tool on Windows to pull it. I mean, you can use, Microsoft has some pretty powerful tools that you can actually inspect memory dumps with on Windows. So that that may be the reason. But yes.
You stated a motivation for your project, your tool set, speed of analysis and speed of response, not so much detection of new malware. Or again, to lower the level of sophistication required when you're analyzing malware. Is that correct?
Yeah, I'm not looking to detect anything new with this. I just wanted to find out as fast as I can whether it's something even interesting enough to put into a debugger, really.
So that said, have you actually found this tool set to be useful in an operating environment, actual live malware that hasn't otherwise been reverse engineered? Using tools such as other forensics tools and disassemblers are not. It is a bit of an art, but it's not rocket science still. So again, speed here seems to be one of the advantages.
Right. Speed and fast response, but also a matter of convenience. And you asked, if I found this useful. I have found it very useful in I could tell you one particular example is with the sober worm. A little while ago, everybody was coming out and saying that, sober is going to, reattack on this date and everything. So I went back through my collection of sober worms and I found out, every single date that was in every single one of them. Just to show you, this has been going on for a while. It's been going on for 2 years. So I use the SANET extensively for that, partly because Sober's written in Visual Basic, and that's just a huge pain in the ass to put into a debugger, but partly because I like to be able to just, tweak the date, work it again, see what traffic it's sending, if it's actually sending those requests, and it also gives me a way to confirm whether what I did in the debugger was actually accurate, like the list of URLs that Sober generated. Being able to test. I actually reverse engineered the URL generation routine. So did F-Secure independently, but I actually wrote a Perl script that would implement it, and then I used the SANet to go back and make sure I was correct. So I mean, it's been invaluable to me. Right behind.
You mentioned specific dates. You also said earlier that you were waiting, and it's by default malware that executes.
Right.
You thought about accelerated time schedules for a year.
The question is, do we want to maybe in that 10-minute time frame or something accelerate and find out if it does something this month or next month and whatever? And that's an interesting idea. I haven't done that. You would have to do some more scripting on the Windows side, but yeah, you could certainly do that. This is interesting. I'm ignoring this side of the room here. Where are we at? Over here.
Are you familiar with Jamie Butler's work in IE for fixed memory?
Yes.
Have you tried this against that?
I haven't actually gone and taken it, mostly because on the Shadow Walker stuff you're talking about, right? The Shadow Walker code, for the most part, hasn't been actually released. There's been snippets of it released. So the whole thing as a rootkit, though, I don't think has been released yet. But from what I've read about it and how it works by basically subverting the translation look-aside buffers, I don't think that this would have that effect because we don't care about the translation when we're reading from the physical memory. We're just saying, give me this page, give me this page. We don't care what virtual address that had. We just want all the physical pages. So I don't think it would have any effect. Do we have any questions? I've ignored this end of the room here. Yes, sir.
Your pristine environment there for the sacrificial lamb box,
Yeah.
market, whatever, it was pretty pristine.
Right.
Is there common client software you usually load onto these?
You could. I mean, I haven't found that it's necessary. I mean, it's possible that the bad guys.
Like through instant messenger program or something.
Right. If you want to look at something, and usually when I put something into this environment, I know already kind of what it is, what kind of threat I'm looking at. I just want to get some more information on it. So if it was an instant messenger type of worm, I'd have to go and load this up with an instant messenger. And so you can do that. You could maintain multiple images if you wanted. I mean, it could turn into a fairly large project. Since I don't rely on it solely, I haven't taken that extra step, but you sure could.
I mean, the malware can say, this box doesn't have instant messenger,
it sure could.
BitTorrent. This is a fake box.
It sure could, and that's kind of the thing where we say that it's not 100%, but between this and having reverse engineering, finding out there's a lot more code in here, in my debugger than this is actually performing. So I need to find out what it's looking for and then go back to it and add whatever it's looking for. So you can.
Do you use patched or unpatched OS as your sacrificial system?
Both. I mean, it depends on how you want to do it. I mean, I haven't found that malware looks at patches all that much. I mean, when it comes to exploiting that OS, sure, it's really important what patch is on it. But when it comes to just running on it, they usually don't care. They usually actually just want to, fiddle with the firewall settings or something like that. But they typically don't care what patch level it's at. In the middle, we.
Based on like network attributes such as hop count or something, couldn't it tell that it's not really talking to something out on the internet and use that as a basis for detection?
Yes, it definitely could. It could look at this network connection and say, hey, what's the deal here? These packets are coming back too fast. When I send something, to a network at AT&T, I get the same responses I get back from China. So at this point, this is going to become a cat and mouse game if people take it to this level. And I, offhand, what I would do to counteract that is probably write a kernel module that would go in and randomize response times and time to list and stuff like that. So I mean, you could play this game, sure. I'm wondering if the bad guys will even bother. So that's great. See, I don't have to write that. That's awesome.
Along those lines, could ADAS be an avenue for protecting your behind the system? taking something, name that's resolved and realize that, okay,
Yeah, that would be an easy way, and that's something that's that's a good point. Is that you could just say, I know that this name doesn't exist. Let's look it up. If I get something, I'm going to scan it. It's an easy way. So.
pass the traffic and then just catch everything with your gateway anyway.
Oh.
DNS traffic, I mean, or just like cache feeds.
I've thought about that, but I look at the scenario that you're talking about as being very low risk right now. They sure might try it, but right now I haven't seen any that try it. And if they did, we'd know something was up when they requested a name and then just never did anything. So we'd look at it and find out they were doing it. We'd know when eventually that they did this. But I don't like the risk of them being able to tunnel things over DNS that I don't want them to tunnel.
Why not just have a real address on your gateway connection?
You mean, but I still have to proxy the DNS in some way. I don't want them to tunnel any information at all. I mean, there might be something in that name that they're using as they're tunneling back some information about, and I just don't want them to have it. So, yes, I've seen it several times. I'm fully in tune with that, and that's why I'm so paranoid. Dan made me paranoid. All right. We are at 10 minutes left, so we got plenty of time for questions. Jeez. Back there.
Do you provide any way of discovering like polymorphic techniques?
If a virus got installed, the question is there any way to if there's anything provided to discover polymorphic techniques? If the virus installed itself and then morphed and then tried to infect another machine, I mean, you're only going to see bits and pieces of what happened in this analysis. I mean, you're not really going to know that malware changed itself. So in that aspect, really no. Scanning the room. All right, I think we're all out of questions. So thank you. Appreciate it. The thing that I used to dump the memory or analyze it? I use DD to dump the physical memory to disk, and then to analyze it after.
On the victim machine, it's running Windows. Do you dump the memory out of that?
Yeah, on the victim machine, it's actually running DD right before it reboots. The pristine OS has been infected. Right before it reboots, it runs DD. It gets just the physical memory dump. And then I have it for later analysis, because it just saves it. It does.
It dumps it on the NAS disk?
Yeah, it's right there, and so when we mount it later, we've got that memory dump.
About Shadow Walker. I don't claim to completely understand memory management in Windows.
Okay.
Of course, that means I very much don't understand. But it's my understanding it operates by synchronizing the caches used for reads versus the cache used for executes.
Right.
And that if you just do complete physical mental fall victim to that. But the workaround is to instead map the page